In this video, we're going to talk about power rule and product rule. Now, I'm just going to go over some examples. I'm not going to talk about the proof like we did in class. The proof is in the book. It might be a good idea to look over it. You are not responsible for the proof. You're never going to have to recreate it either on a test or quiz or on the AP exam. But, you know, it's always good to know why something works and where it came from. Essentially, the power rule says that if I'm taking the derivative of x to a power, I simply drop the power out front as a coefficient and then subtract 1 from the power to get my new power. So, for example, this first one here, the derivative of 3x to the fifth, well, we multiply 3 times 5, so we get a new coefficient of 15. Okay, we still have x, but then we drop the power by 1, so it becomes 15x to the fourth. The next term, 6 times 2 is 12, and now we have x to the first. Now, of course, normally we wouldn't even write a first power. We would just say 12x, but that's the derivative. Next, f prime of x, 3 times 5, so we have 15x squared minus 4 times 2 is 8. Drop the power by 1 plus. Now this is kind of an interesting case. 7x, so essentially the power is 1. So if I do 7 times 1, I get 7, and then I drop the power to be x to the 0. Well, x to the 0 is just 1, so it becomes 7 times 1, which is 7. And then remember from our work earlier that a constant, minus 6, does not affect the slope. So it's actually not part of our derivative. So if you want to think about it this way, kind of an offshoot of the power rule, think about the fact that this was like 6x to the 0, because there wasn't an x there, so x to the 0 is 1. So when we multiply 6 times 0, it's 0. X to the negative first, which is 0. And along with that, this last one, f prime of x, since it's just 3, it's just a constant, the derivative is 0. And graphically that should make sense, because f of x equals 3, if you graph that, it's just a horizontal line at 3. And remember, the derivative is a function that finds the slope. Well, what's the slope of a horizontal line? It's 0. Some other ways we can use power rule by just starting off with a little rewriting. For example, the square root of x I could rewrite as x to the 1/2 power, and 5 over x squared I could rewrite as 5x to the negative second. So now when I do my power rule, I get 1/2 x to the negative 1/2, because I'm dropping the power by 1, so 1/2 minus 1 is negative 1/2, and 5 times negative 2 is negative 10, and we drop the power, so it becomes x to the negative third, like that. Now we usually like to rewrite these with positive exponents. So I could rewrite my derivative as 1 over 2x to the 1/2 minus 10 over x cubed. Right, just getting rid of those negative exponents. Again, negative exponents always put us in the denominator, so that x to the negative 1/2 goes in the denominator, x to the negative third goes in the denominator. Even better, since the original problem had a root in it, let me rewrite my derivative with a root. So it'll be 1 over 2 square roots of x minus 10 over x cubed. Okay, that would probably be my best looking derivative. Next, we could start by rewriting this problem as we can leave the 6x to the fourth, but instead of 5 over x, let's write 5x to the negative first. Okay. So the derivative at 24 x cubed. Negative 5 times negative 1 is positive 5. X to the negative second, dropping the power by 1. And the derivative of minus x is just minus 1. And if you had any problems seeing that, I think the easiest way to look at it is just remember that coefficient's 1 and power's 1, so 1 times 1 is 1, and then the x becomes x to the first becomes x to the 0. Let me rewrite this with without the negative exponent, so 24x cubed plus 5 over x squared minus 1. I think that will be our best looking derivative. Finally, 8x plus 9 over x cubed. This one certainly doesn't look like it's very doable with the power rule, but we could rewrite this by splitting the numerator. We could write it as 8x over x cubed plus 9 over x cubed. Okay, and because we have this common denominator, right, we just add the numerator and put it over the denominator. We become 8x plus 9 over x cubed. Well, we could rewrite again, because 8x over x cubed is 8 over x squared plus 9 over x cubed. And now let me rewrite it without those negative exponents, or with negative exponents. So without the fractions, 8x to the negative second plus 9x to the negative third. So the derivative would be negative 16 x to the negative third minus 27 x to the negative fourth. So I could rewrite that with some positive exponents, negative 16 over x cubed minus 27 over x to the fourth. The product rule, you can see up here, and again the proof is available. I'm just not going to do it in here. But essentially it says if I have two functions being multiplied together, I simply do the first times the derivative of the second plus the second times the derivative of the first. So in this first example, I've got x squared plus 1 multiplied by x cubed plus 3. I'm going to make x squared plus 1 my first. I'm going to make x cubed plus 3 my second. Okay, so the derivative is first function times the derivative of the second function, which would be 3x squared, plus the second function times derivative of the first function. I can multiply this out. I have 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x, which I could simplify to be 5x to the fourth plus 3x squared plus 6x. Now, that's the derivative. This is not the way I would do this problem. I thought it'd be good to see it with a simple example. But how I would have done this, I would have gone back and instead of doing product rule, I think right away I would have multiplied this thing together. You know, I would have done x squared times x cubed and had x to the fifth. X squared times 3 is 3x squared. 1 times x cubed is x cubed. 1 times 3 is 3. And then I would have done the derivative of this just with power rule. And just look, the derivative of x to the fifth is 5x to the fourth. The derivative of 3x squared is 6x. The derivative of x cubed is 3x squared. The derivative of 3 is gone. I think that would be easier. But there are sometimes we don't have that luxury. For example, the second problem, if I made the first function 7x, and I made the second function cosine of x. There's not much we can do with that. So we have to just go for product rule. So we've got the first multiplied by derivative of the second. Recall derivative of cosine is negative sine. Plus the second multiplied by the derivative of the first, which is just 7. Not much more we can do with that. We usually like to have our trig functions come second, so I'm going to write this as negative 7x sine x plus 7 cosine x, and say that that is my derivative.